There are several ways of characterizing the phase response of discrete time filters. We have the frequency response, of course, h of e to the j omega of the filter, which tells us how the filter acts as a function of frequency. In other words, if a sinusoid comes in of a certain frequency, a sinusoid goes out of the same frequency, but its amplitude gets shifted by the magnitude of h of e to the j omega, and its phase gets changed by the angle or the phase of h of e to the j omega. Now, the first thing we need to observe is that the phase of h of e to the j omega is not uniquely defined, because I can take the phase, writing that as e to the j angle h of e to the j omega. I can add any integer multiple of 2 pi, and I have exactly the same phase. So the phase is not unique. So we're going to define the phase in two different ways. We're going to define the principal value of the phase, which is signified by capital ARG of h of e to the j omega, and that's the value that we would compute numerically, and it's going to be between minus pi and pi. So that's the principal value of the phase. So if I had an angle for a phase angle of negative 4 omega on the interval minus pi to pi for omega, then the phase is going to go from 4 pi down to minus 4 pi. But if we take the principal value of the phase, then it looks like this green curve here, where it starts at 0 and then goes negative, and then there's a jump of 2 pi, and then it has again a slope of negative 4, and we get another jump of 2 pi, and so on. And we can also define the unwrapped phase, which we're going to denote by lowercase letters arg, h of e to the j omega. And in this case, this would be just the phase going from 4 pi at omega equals minus pi to minus 4 pi at omega equals plus pi. And this case, we've got the phase as a continuous function. These jumps that we had here of 2 pi have been removed. So to unwrap the phase, we remove any jumps of 2 pi. So we have the case of linear phase, where the unwrapped phase takes the form negative omega times n naught. And in this case, if the magnitude response of this filter was 1 at all frequencies, we would just be taking the input and delaying it by n naught samples. And in general, we can have n naught be a fractional like 2.5 or something, or 6.8, and we still consider that no distortion. And we can extend this idea to generalized linear phase, and this allows us to accommodate certain common cases that arise where the system still has, for the most part, a nearly distortionless response. So a generalized linear phase system can be written in this form here as a of omega, where a is a real valued function but can be positive or negative, times e to the minus j alpha omega plus j beta. So beta is a constant and doesn't vary with frequency, and this is a linear term, alpha omega, and if a of omega changes sign, then we're going to get a jump in the phase of pi. So for example, if we take a of omega to be cosine of omega, and we set alpha equal 2.5 and beta equal to 0, well then the phase has slope of negative 2.5 in this vicinity near 0, because the cosine is positive in that region, a of omega. But when a of omega changes sign, which it does at omega equals pi over 2, at that point the cosine becomes negative and the phase takes a jump of pi. So we have this linear slope, but the phase can have discontinuities of pi associated with sign changes in a of omega. And then of course we can have the case where the phase is nonlinear. What happens with nonlinear phase is that the different frequency sinusoids basically experience different delay through the system. In linear phase, sinusoids going through the system experience the same delay at every frequency. And therefore, when they add up at the output, they produce the same shape that they did at the input. But when we think of a Fourier decomposition with nonlinear phase, the sinusoids add up in a certain way at the input. Because different frequencies experience different delays, they won't add up in that same way at the output. A useful way to characterize phase distortion, in particular nonlinear phase systems, is with something called group delay. And group delay is defined based on how much delay the system imparts as a function of frequency. So we're allowing different delay at different frequencies because the system could have nonlinear phase, and group delay is a measure of this. To develop the idea of group delay, we're going to consider a narrowband signal S of n, a very low pass signal. Now we're going to take this low pass signal and we're going to modulate it up to some frequency omega naught, as I've shown here. We can do that in the time domain by multiplying by e to the j omega naught n, and what that does in the frequency domain is it introduces a shift replacing omega by omega naught. Now I'm going to apply this signal to a system that has nonlinear phase. We'll assume for the moment that the magnitude response of the system is unity, and that our phase response looks something like this. Now the phase really doesn't matter except where the signal has frequency content. So in the vicinity of omega naught is the only place that the phase really matters if we're going to put this input in. And what we'll do is we'll approximate our nonlinear phase with a linear description in the vicinity of omega naught. So we'll have the value at omega naught, which is phi naught, then we'll calculate the slope of the phase, and we'll call that tau of omega naught. And then if we multiply that by slope by omega minus omega naught, we've got a description for the local phase here. And this slope parameter, tau, viewed more generally as a function of omega, is called the group delay. And it is negative the derivative with respect to frequency of the unwrapped phase h of e to the j omega. So let's see why we call this a group delay. We'll apply this particular input, x of e to the j omega, with frequency content in the vicinity of omega naught. We'll apply that to the system. The output then can be written as x of e to the j omega, that I'll write as s of e to the j omega minus omega naught, times e to the j, this phase term where we're using the linear approximation. So I have e to the j quantity phi naught minus tau of omega naught, omega minus omega naught. We can combine some terms here, pull the e to the j phi naught out, and I have s of e to the j omega minus omega naught times e to the minus j tau of omega naught times omega minus omega naught. This term here involves omega minus omega naught. So that's like a modulation. So we had modulated S, we can view this as a linear phase term that's been modulated up to omega naught. So if I take the inverse discrete time Fourier transform to get a signal y of n, I can write y of n as, I have this phase factor, e to the j phi naught, but then I've got my time delayed system which has been modulated to frequency omega naught. But the time delay is given by tau of omega naught. So the group delay, what it's telling us is at a particular frequency what the time delay is experienced by energy or frequency content in that neighborhood. So we can say that this group delay tells us the delay experienced by a very narrow band envelope of a signal centered at a particular frequency, omega. Clearly, if I have a linear phase system, then the derivative is going to give me a constant, and I'll get a constant group delay, and that's because all of the frequency components experience the same delay. In general, with nonlinear phase, I'm going to have a non-constant group delay, and different frequency packets will experience different delays. So let's look at an example of this. And I've chosen an all-pass system that has 8 poles at 0.95 j on the imaginary axis, and similarly 8 poles at minus j 0.95, and then it has 8 zeros at 1 over 0.95 times j and minus 1 over 0.95 times j. And because these poles and zeros occur in conjugate reciprocal pairs, we know that the magnitude response of this system is 1. So this system will introduce no change to the magnitude of the input of the system. But the phase is rather interesting, and what I'm showing in this top panel here is the principal value of the phase between minus pi and pi, and then we've unwrapped the phase in the middle panel. You can see that the phase is close to 0, and then as we get near pi over 2, as we move around the unit circle in the vicinity of where these poles and zeros are located, the phase plunges rapidly as a pretty steep slope, and then it flattens out again as we get over here towards omega equals pi. So the group delay is going to be the derivative of this curve as a function of frequency. You see that in this low frequency region, the curve is basically flat, so the derivative is going to be 0. But then where it gets real steep in here, the derivative increases, and at pi over 2, we're getting over 300 samples of delay. That if I put in a signal whose center frequency is pi over 2 and extends some narrow bandwidth in that vicinity, it would experience approximately 300 samples of delay. Whereas a signal at lower frequencies would experience virtually no delay, or similarly at higher frequencies, that signal would experience virtually no delay. So this is a pretty nonlinear phase system. So what we've done is take and generate an interesting signal for this particular system. We put a modulated sinusoid with frequency pi over 2 for the first 150 samples, and then the second 150 samples we have the same sort of modulated sinusoid, but in this case we've got a center frequency of pi over 8. So remember, the group delay tells us that this signal with the center frequency of pi over 8 basically should not be delayed at all, and this other higher frequency component, which has center frequency pi over 2, that's going to be delayed on the order of 300 samples. So if I take an input like this, I should expect my output to have this first term delayed and start at around sample 300. And indeed, that's what you see when you pass this input through this all-pass system. Now there's a little bit of other distortion. That's because our analysis of group delay was idealized, and this signal has some bandwidth which is not 0. So some of those terms at the frequency edges are going to see less delay than the 320 samples or so that's experienced at pi over 2. But nevertheless, you see that these two components are delayed differently through this system. This component at pi over 8 experiences virtually no delay. We've got 300 sample delay for this term, and so they've flipped ordered. And that's just showing how nonlinear phase moves the frequency components of a signal such that we can get different shapes at the output compared to what we have at the input. So linear phase systems are not going to do this. We're going to have the output is going to take the same exact shape as the input, just a delayed version. But with nonlinear phase, we get distortion because different frequencies experience different delay through the system, and group delay is a convenient way of representing how different frequencies are affected.